So the first 3D segmentation model that I read about was 3D U-Net, but it was an attempt at beating the 3D U-Net, so they talked about different variations of it, and the variations were quite similar, though there were some things that were distinguishing between them. So the first model that you see is the plain 3D U-Net, which is the original one, and then you have the second one, which is the residual 3D U-Net architecture. And the thing that's different about both of these is this one, this is a very small thing, but this one has leaky ReLU and this one has ReLU function. And then this one doesn't have any residual blocks, but this one does. So here in the residual blocks, you have, instead of it being a convolutional and then instance normalization and then leaky ReLU function, it's actually repeated 2 times. But instead of leaky ReLU, it's a ReLU activation function. So it's convolutional layer, instance normalization, ReLU, convolutional layer, instance normalization, and ReLU. I was really interested by this because I don't know why they wanted to make the model deeper, because it would obviously have more computations, and then there was the vanishing gradient problem, which I'll also talk about. So I was really curious about that. And what I found out was there's this whole reasoning behind why they did what they did, because I didn't really know what residual blocks were. So I decided to go deeper into that too. But before I go into that, another model that they talked about, and they don't have the diagram for this, but it's called the pre-activation residual 3D U-Net. So instead of the residual U-Net, now instead of the architecture of conv instant normalization ReLU, conv instance normalization ReLU, you now have the instance normalization and ReLU put in the front, and then the ending is a convolutional layer. So now onto the residual blocks. I really found this interesting because there's this whole architecture called ResNet, and I knew what ResNet was, but I didn't exactly know what the residual blocks were. And it's really cool to see how they wanted to incorporate the residual blocks and these skip connections that are special, and how it comes to play to solve the vanishing gradient problem, despite the fact that the depth in the residual 3D U-Net architecture is huge. So, in terms of the research paper, which was called Deep Residual Learning for Image Recognition, it talked about the vanishing gradient problem, which I've said a lot in this video. Now, the vanishing gradient problem, what happens is when you want to find the error rate so that you can do the backpropagation and update the weight values again, what happens is you have to find the derivatives. Now, to find the derivative between the first block and then the last block to find the error rate, what you need to do is follow the chain rule. And the chain rule is you find the little changes, the derivatives between this and this, and then this and this, and then this and this to get to the end. And then you perform the backpropagation. Now, what derivatives and the fact that you have, let's say, activation function that sometimes can squish the value. So if you have a sigmoid that squishes the value of whatever the weight and the connection plus the bias equals, it basically squishes it into 0 to 1. So that's a very small number. And if you are performing chain rule, which means that you have to multiply these little changes to get to the end, you're going to get a very small number because of the fact that you're multiplying very small numbers in the beginning anyways. So in the end, you get a very small number, and when you want to update the values will only update a bit because those values are small. So then the accuracy would be worse too. So all in all, what happens in the correlation you have here is the larger the depth is, the more depth you have, the more layers you have in the neural network architecture or the model architecture, the worse your accuracy is going to be. So that's a correlation. And that's what the vanishing gradient problem is all about. Now, of course, there are some things to mitigate this, and some of these include normalization, the ReLU activation function particularly, and residual neural networks. Now, residual neural networks for deep residual learning, what's happening is now when you have this architecture over here, which was in Andrew's video, very famous for his course on Coursera, what he added in his video is this very simple explanation of the without the residual blocks, what happens is first you have, again, that input layer, then you have a linear layer where you do the weights times the connection plus the bias, and then you move on to the ReLU activation function, and then now again you have the linear and the ReLU, and then you get to the end. Now, with the residual block, what actually happens is you keep the same thing. So you have the exact same size, except now you're adding this thing called a shortcut or a skip connection, which is an arrow. And the arrow goes from before you go to the linear function, so the input that you have before the linear, and then you go from there and you go all the way to right before the ReLU activation function. So there's different benefits to this. First of all, you see that the information is skipping over these linear, the ReLU, the activation, the linear. And then before it goes to the ReLU, it just adds and concatenates. So you are finding the value over here, going from here to here, but you're also finding it from here to here, and then you concatenate it right before the ReLU. So obviously, you have that skip of information. Another thing that's happening is because you're skipping over this activation function, you're not having that sort of sigmoid or whatever the activation function is supposed to be. It's not being applied to that specific weight or that result you get before the activation function. So you're skipping over it completely, which means that it's not squishing the value. So when you're going from here and you're going over here, you don't have a gradient that's vanished because you didn't apply that activation function. So when you add it, you just don't have that vanishing gradient problem. And then you move on to the ReLU, but obviously it's so much better because you're taking it from here, you're not applying it from here, and then you're just adding it and then you're going through with it. Now, if you think about it in this sense, what happens, and I already mentioned this with the chain rule, is you multiply the values and then you keep multiplying it. But over here, you're skipping out on one activation function completely. So that's a whole different way to mitigate the vanishing gradient problem. I think I've gone through pretty much everything. It was a very interesting paper. They looked at how it compared to the C410 dataset, how it looks with the, what was it? It was they basically just explained the plane model, not the U-Net. This paper that I'm looking at right now, this is the just how does deep residual learning work. But in this one, the deep residual one, they they looked at the comparison with the C410 dataset, the COCO dataset, I think it was. There was a lot of datasets that they tried out and they saw that it worked really well because it's, I mean, it's pretty counterintuitive to say that the training is the error is going to decrease if there's a lot of depth. So it's pretty counterintuitive to say that. But now that you have all of these features, you have the batch normalization happening, you have the residual block, all of that just goes against it. And I found that really interesting because the depth really helps a model. It really helps it try to find out what the features are in the image, how to understand what's in the image as a whole, and do the task at hand, whether it be classification, whether it be segmentation, which is the one in my case. So the extra depth helps a lot. And if you're preventing the vanishing gradient problem, then it's an extra thing, right? And it's just beneficial overall. So that was pretty much it on understanding how the residual learning ties into these models. And going back to the models, actually, now what's happening is you can't see this on my paper. I like to print out the research papers that I read just so it's easier for me to draw it out. But now what's happening is you have the input in this case. And then right before the 3D convolutional, that's where the arrow starts. And then it goes from there all the way to right before the ReLU activation function that they're going to be using over here. So what's happening is here, you'd have the arrow here, and then it would go from here all the way over here. But then you're still performing all of these steps. And then you're going to be concatenating over here, and then you'll go through the ReLU. And that's going to be repeated a few times. So over here, what's happening is you have the normal 3x3 convolutional instance normalization ReLU. feature block that you have here, that's always there. It's always pretty much constant in the first place. And then over here, you start off with the residual block, and then you have the stride on 2, just so that you can increase the amount of channels but decrease the dimensions. So you can see that it goes from 24 channels to 48 channels, but the dimensions decrease from 160 to 80, and then it follows that same thing. Over here, you have the residual blocks that are repeated a couple of times. That's just an architecture that they used, and they found that pretty accurate. And know that this is only for the encoder part. The decoder part stays the same in both of the models. That's pretty much it for the first 3D segmentation model.
The second research paper that I looked into was HDC-Net, and it talked about obviously the model that it implemented and worked on to get a fairly high accuracy. But the thing that was really intriguing about this one was that it talked about different models, different related work, what the status quo is, and then how it surpassed the status quo. So it's really interesting for me to go deeper into some of the related work and look at some of the models that already exist and how they perform and the different architectures that they have. And the thing is, there's so many types of ways that you can segment tumors. It's actually crazy. There's cascaded neural networks where you have sequential models of doing one thing, and then you have another model for doing the other thing, but it's all related in a sequence. There is one for curriculum learning, which is when you're actually training the model, you're starting off with relatively easy examples, and then you're going to the harder examples from there. So if you wanted an example of this, let's look at the segmentation. Let's take that as an example. So you want to segment out the whole tumor, the tumor core, and the enhancing tumor. So obviously the whole tumor would be the easiest to segment because it's pretty much the basic outline. And then the tumor core and enhancing tumor might be a bit harder. But what you would do in curriculum learning is you would give the model, when you're training, you would give it the whole tumor first so that it has relatively easy examples to start off with, and then you would go on with the tumor core and the enhancing tumor. Another thing that they also talked about was there was one more. Ensemble learning. And ensemble learning was when you're combining a variation and combination of models, and then you're doing the task that you want at hand. So those were the three main things. However, the thing is, the HDC-Net, what it did was it didn't actually use those different three things of ensemble, cascading, and curriculum learning. It just used a model that went from A to B in one single pass. And there's different reasons for this. The thing is, modeling data all in one go can be a very difficult task because especially when you're expecting really high accuracy for numerous reasons. For example, there might be slow modeling. There also might be a failure of convergence, so you might get a lower accuracy. And those are the two main cons and issues, but the main advantage of a single pass model architecture is the fact that you wouldn't have that many computations, right? Because if you have more models, that's just more computations. And a lot of the times you might not have the GPU power, the computational power for those calculations. So people tend to just go through that. And through the other papers that I've read so far on 3D U-Net, which is a single path, they're not cascading, they're not ensemble, and curriculum learning doesn't really fit into building the model, but it's more for training. Anyways, for both of them, I've mostly seen single pass model architectures. So it was really surprising to see that many cascading architectures. And one of them they talked about was cascading VNet. Now, the way this one works is you have two VNet models. The first one, you take the four channel image, and this basically means that you have flare, T1, T1CE, and T2, and then you're putting this through the first model, and the first model is going to do one task, which is segment the whole tumor. Once it segments the whole tumor, it's going to go through another VNet, which is why it's cascading. It means that it's in a sequence. So you have two in a sequence. Now it goes to the other VNet, as I mentioned, and then it finds the other subregions that's not the whole tumor, that's within it. So the tumor core and the enhancing tumor. And then for the Dyson-Hausdorff metrics, which is usually the metrics you would have in the BRATS dataset, the BRATS challenge, and basically it's the annotation and segmentation for brain tumors. That's essentially the challenge that I've also been working on. So that's what the models are for. For the dice, you see that in the validation set, the accuracy for enhancing tumors 71.4, whole tumors 87.7, and as I mentioned, it's going to be higher because it is easier. And then tumor core is 63.7%. And then you have the Hausdorff metrics as well, but it's just easier to conceptualize what the dice metrics look like. This is another cascading model that was talked about in the paper, which is 3D SE inception networks to sequentially segment the whole tumor. So first of all, you have this, right? This is, again, the FLAIR T1, T1CE, and T2. And then you segment out the whole tumor first. So once you segment out the whole tumor, you pass it on to the first stage U-Net. You go through the U-Net 1, and then you find this one thing, which segments one tumor substructure. Then you go through the other one, and then it segments the other tumor substructure, and then you combine them together by adding them. And that's the concatenation. In terms of the dice and the Hausdorff and other things that they found here, over here, so this is called the inception. It talked about, one second. Okay. There. Okay, so the one for this, actually I don't think this is the right one, but honestly, I didn't really care about the accuracies at that point. My intention mostly is to build as many models as I can that are different, and then we'll see which one has the high accuracy. But for me, it's more about learning. So even if I get to replicate the model, no matter how accurate it is, I'm going to try to make it as accurate as I can. So yeah, I mean, I might go on the basis of the metrics, but this is just for you to understand how accurate these are compared to the status quo or different models that there are available, including the one in this paper. We talked about curriculum learning. In this paper, they talked about having this very novel technique of HDC modules, and they're replacing the expensive 3D convolutionals, which you would usually have where you have you would have 3x3 convolutional, and then you would have another 3x3 convolutional, and then you'd have a bunch of things. Honestly, you'd have the max pooling layer, you'd have the ReLU, all of that sort of stuff is what usually happens in a typical convolutional block, and it is quite expensive. So I was curious to see, what they thought of in this perspective. And the thing is, they didn't use, as I mentioned, they only use that single network. And when they had that single network from going to point A to point B, I guess you can call it segmented, but the word is probably more of decomposed, which is why the model is called HDC. You could also call it decoupled. Now, what that means is that when you have the input, and this is one HDC module, so you see that this is one HDC module. So when you have one HDC module, you have the input, right? You have the 4 channels, which represent the 4 modalities that I talked about in the beginning, and you're just separating all of them. So that's what it means. You're separating all of them. And from there, you would do a set of operations. This is more complex, but they also talked about VDC. And I found this really interesting because they wanted to do this in the beginning. The reason why they didn't go about this after is that because it would be more computationally expensive, plus it would just be easier to do it one by one, where you do one modality, one modality, one modality, and one modality. And then for here, you just take this and you easily just put it at the end. You take this, you only have to do it once, you put it at the end. But for here, you have to do the convolutional layer many times and on every single modality. So in terms of a computational perspective, this one, the HDC, would have just been easier. So that's why they went with that. Now, talking about the HDC a bit, you take this one modality, and then you put it here. You just put it at the end when you'll concatenate all of them together. For this one, you take it, you put it through a 3x3x1 convolutional, then you concatenate. Then you go on to this one. than this one. And then at the end, you have a 1 by 3 by 3 convolutional, and then you output it. Now, there's variations of the HDC module as well, because there was HDC minus, which they talked about, and that was more of taking this and making it 1 by 1 by 3 instead. So that was another approach that they talked about. And there was I think it was HDC plus as well. And there is just many variants just to see which one would result in a better accuracy. So that was pretty much it in that sort of perspective. And from there, just looking at some of the accuracies, you see that these are basically the status quo. So Brat's challenge has been going on for a very long time, actually. And this is just the 2018 one, and they're comparing the results from that challenge. So these are the different types. You see there's cascading, there's ensemble, there's single passing through one. And then here you see the 3D U-Net, which is the plain one, the V-Net, which is also really good in terms of the status quo. Now, obviously, it's 2018, so the numbers might be different based on the new and modern components that we have found in 3D segmentation and semantic segmentation models in general. But in terms of the HDC-Net, you see here that in terms of the whole tumor, the tumor core, you see that it had a fairly high accuracy of 84.7%, which was apparently the highest in this category. And then for the HDC plus, you see that the 81.5% here was the highest in this category for the enhancing tumor. So in that sort of perspective, you can see that these models are actually really accurate. And yeah, I mean, this was pretty much the second paper that I read. The next model paper that I read was the H2NF-Net. And the reason why it's called H squared is because this model of HNF, the single HNF-Net, is actually repeated 2 times consecutively, which makes it a cascading model. So specific to the HNF-Net, which is the single net, what happens is, first of all, you have this model over here. This is the single one. And then this is the one where you add it twice, but we won't go too deep into that. Anyways, for this first one that we look at, you start off with that same input of the 4 modalities, which again is T1, T1CE, you have T2, and you have flare. So first of all, the way it describes it in the paper is you have 5 scales that are mentioned, and those 5 scales are represented by the R. And if I zoom in, it might be easier. So you have the R divided by 2, R divided by 4, R divided by 8, R divided by 16. The reason why you have this is because when you have these arrows that are pointed downwards, you're downsampling by 2 because the stride is 2. And so you go from the size being R to R divided by 2. But then at the same time, obviously, you're also increasing the amount of channels because that's just how the models are supposed to work. So you increase the amount of channels while decreasing the dimensions. The model is very different from a regular 3D U-Net or V-Net because if you look at it, there's 2 different things that are going on. So in respect to the R, you have these 5 different scales, and the green there's the green, which is represented by the R, there's the yellow, the blue, the pink, and the orange. So you already have these things. Now, there's one thing that's happening at the top. Now, the way they describe it in the research paper is, this is where it got really confusing for me. I actually don't understand this very well because I think what it might be is a problem in terms of the misunderstanding, and it's a bit vague on their side too, because they mentioned that at the original scale R, which is this part over here, there are 4 convolutional blocks, 2 for encoding and 2 for decoding. It implies later on that the decoding is this part, but this only has 1 convolutional block, which over here is the 3x3 convolutional plus the batch normalization plus the ReLU activation function. So you have 2 here, but you have 1 here. So what's really confusing me is that they said that there's 4, but here I see 3. And then there's also that confusion of, if you have two here, are two of them going over here and then they're increasing the amount of channels that you might have or something like that? What's exactly happening here? This is also pretty vague in terms of what parts of the image are going through the PMF modules, which is a huge part of this because they're cascading. Now, aside from this, one thing that we do know for sure is that there's the connection from the encoder to the decoder, which is from here to here. And for that, you're skipping the processing that's happening in the middle over here with the PMF modules, and then you have the EMA module. You're skipping all of that to go from here to here. By doing this, what you're doing is you're maintaining the high resolution that you have over here in the beginning, and then you're also maintaining the spatial information that you have that would be beneficial later on when you're concatenating after going through the PMF modules. And speaking of the PMF modules, you're using them to also do it's mostly feature extraction, right? Like you would usually do in any neural network model. So you're trying to do the feature extraction, find out what's happening in the image. And at the end of the last MF module, all the four scales, you can see that they're going back to this over here, the R/2 scale. So there are two parts of the PMF module that it talks about. And the first one is the parallel multi-scale convolutional block. So the parallel multi-scale convolutional block is, you see these parallel, I guess you can just call them parallel blocks. You can tell that they're straight over here, right? You can see that they're aligned pretty much. So the parallel ones are the ones where it just goes straight like this. And then there's these other ones that are fully connected fusion blocks where it kind of acts like a fully connected layer where there's these connections between those blocks. And you see this happening mostly in the middle of the PMF modules. So again, what it's trying to do there is just trying to find out what's in the image. And the former, which is the parallel multi-scale, it has repeated residual convolutional blocks at specific scales. So what that means is that you see here, you have it's similar pattern of it being 1 and then you have 3 and then 1, 3 and then 1. So that itself is residual, and it talks about it here as well because in residual neural networks, I guess this is batch normalization. You would have some sort of normalization. In the previous model that I looked at, it had instance normalization. But here you have that same pattern of convolutional normalization plus value, convolutional normalization plus value, and then you have that sort of skip connection going from here to here right before the last value activation function. So that's what's happening in most of that. And again, that's just trying to find out what's happening in the image. Over here, what it says is that in the fully connected fashion, you're having the branches as the summation of the output features of all the resolution branches. So that's pretty much it of you're trying to find more information. But what it really comes down to in trying to find what's at the end is when you concatenate all of these, as I said, at the R/2 scale, you actually go through the EMA block. And the EMA block module, it's essentially aggregating all the contextual information that you get over here. When you do this, when you have the parallel information at the different high resolution features, and you have the fully connected fusion block, which is getting all the contextual information, you're gathering all of them at the EMA module. It's basically summarizing all that information, and then it's doing feature reconstruction so that when it goes over here, which is the end result, and then you have this, I believe it should be some sort of you have this sort of trilinear upsample, which is 1 by 1 by 1 convolutional. You go to it being 32 channels so that you can easily concatenate it with the connection that you have from here. And again, as I mentioned, they haven't specifically specified what sort of transfers there, because they did say 2 blocks at the encoder, 2 blocks at the decoder, but it's really ambiguous. So, anyways, when you concatenate it, which over here is the element-wise sum, as you can see, you have this, and then you put it through a sigmoid activation function, and you get the output. So that's what's essentially happening. This is also a bit more about the EMA module. I didn't focus on this too much. It was more of just understanding what sort of architecture they would look for. And although there were things that I was a bit doubtful about, what I really got out of it was how people, or I guess how the developers or the authors in this case, really structured it in terms of taking the input and having a skip connection all the way till the end. So you preserve that while also calculating the new information and trying to get the model to learn, and then add that together. And then it summarizes a lot more of the conceptual information and the spatial information that you get, which would then lead to the segmentation in the end. Now, with the cascading model, it's pretty much the same thing, except now, once you go through the sigmoid, you actually go back and you go to the concatenation, where you concatenate over here, and then you do the same model again. It's basically the exact same. So that's what I mean by cascading, because it's going in a sequence. That was pretty much the third paper that I read.
The next paper I read was nnU-Net for brain tumor segmentation, and this was done by some workers at NVIDIA, and they got first place in the BRADS 2020 challenge with a dice score of 88.95 for the whole tumor. For the enhancing tumor, they got a dice score of 82.03, and for the tumor core, they got a dice score of 85.06, and so they came first place. Going through a bit about the model, what they wanted to do is they actually didn't have that many specific or modern components that other models would have. It wasn't a cascading model, it wasn't an ensemble, it's just a simple single network architecture of the 3D U-Net, except there are some accommodations, but really there aren't any variations. So going into the model, it's fairly simple actually. You start off with the four modalities, which are 128 by 128 by 128 because you resize them. And then you go through the encoder part of the model, which is the left side. And you have the 3 by 3 by 3 convolutional plus the instance normalization and the leaky value function. And this is what the leaky value function looks like. And if you wanted to know what a ReLU function looked like, just pretend this leak wasn't there, like it wouldn't be pointed this way, it would just be straight. It would be completely horizontal, and then whatever is negative becomes a zero, whatever is positive stays as the same value. So after the leaky value, you have this pattern going on again and again where you also have the downsampling, and then you have the bottleneck over here, and you're going back up with now, I mean, it's the same thing. The blocks are the same, it's just now you have the convolution transposed. And that essentially means that here, when you're decreasing the size of the image, you're going to increase it again. And here, when you're increasing the size of the channels, you're going to decrease the size of the channels. And the intention of the output would be to have a shape that is 128 by 128 by 128 by 3 by 3, because you have the enhanced tumor core, you have the you have the enhanced tumor, the whole tumor, and the tumor core. So you have those three classes. So you want 3 channels. Now, after they talk about this, what I got the most out of the paper was how they trained the model and how they found out how like the comparison between the dice and the Hausdorff distance. So these are the annotations that I did on the research paper that I printed out. But essentially, when you're provided with the BRADS challenge, you have certain labels. So if you look at the segmentations, and I don't have my code open right now, otherwise I would show it. Essentially, you have 4 labels that are given to you. You have the background, which is given a label of 0. You have the non-enhancing tumor, which is given a label of 1. You have the peritumoral edema, which is given a label of 2, and you have the enhancing tumor, which is given a label of 4. So in total, you have 4 labels. Now, the task, however, is to come up with segmentations for the enhanced tumor, the tumor core, and the whole tumor. And in order to do that, because these 3 classes, they have they have a combination of the labels, right? So if you look at the whole tumor, it has a combination of all 3 classes, all of edema, non-enhancing, and necrosis, which is what it's called. You can call it anything else as well. And then the tumor core is the non-enhancing plus the necrosis, which again, it's you can say necrosis or you can say the peritoneal edema. Though necrosis is easier to say, and then you have the non-enhancing and then the enhancing tumor for the tumor core, and then you just have the enhancing tumor by itself. So what they did is you just, instead of thinking of it as a combination of the labels, you just think of it as one thing. So now you have 3 segmentations and you're not really worrying about the labels that were provided in the beginning. So that's why you have now multi-binary segmentation tasks. And the way they approach this is after you finish the model over here, you have a softmax function. Now, one thing that the paper was a bit that I guess baffled me a bit about the paper was the fact that here it said that because it was binary and such, they wanted to make the activation at the end be a sigmoid instead of softmax, because a softmax is usually used for multi-classification. So you have probabilities for all the classes, which in this case would be 3 because you have 3. And then the sigmoid would just be the binary. Now, they say sigmoid, but in the architecture, they actually write softmax. And looking at other papers, they also wrote softmax. So what I am going to do is I'm going to assume that sigmoid was just something that they might have wanted to show that you could also do. And you could also do that, but it just doesn't make sense because you have the enhanced whole tumor and tumor core. So you have 3 classes. You don't have 2 classes. Otherwise, yes, you could have used binary classification. But even then, even if you had 2 classes, they would have to be the background and one other class. It can't be the enhanced tumor and the tumor core, for example, because the background also counts as one class. So technically, you have 4 classes. But I mean, when you're doing the Argmax function, which I'll talk about, you're only having in particular 3 channels for those 3 classes. So let's pretend in that case, if we just pretend this doesn't really exist, because they probably wrote something wrong, to be completely honest. So if you do the softmax and then you do the argmax and then you do the binary cost entropy loss. So that's how it would work essentially. After the softmax, right, you end up with that 3 by 1 by 28 by 1 by 28 by 1 by 28. So argmax, what it does, and this is a really good visualization of it, is let's say you had 3 channels. It goes through pixel-wise probability. So it looks at the same pixel, just in different channels. So you're looking at 3 pixels at the same time. And you're putting the argmax function over it so that whatever the maximum pixel value is, that's what's going to be given the value of 0, and then the rest is going to be given the value, the maximum will be given the value of 1, and then the rest will be given the value of 0. So whatever has some sort of, I guess, tumor subregion happening would have that 1 in its channel. So then at the end, when you go through all the pixels, now you have 3 different channels, and you have those 3 different subregions, which would hopefully be the case if your model is accurate. So now what you could have done is you could have just taken apart all of the channels, right? Because you're already done with them. You're already done the argmax. You could take them apart. So you'd have 120 by 120 by 1, 120 by 120 for one, and then 120 by 128 by 1 for the other one. So you have 3 of them. And so now you can use the binary cross entropy because you're trying to find the loss the difference between the ground truth and then the subregion that you actually try to segment with your model. And from there, you would basically be able to find the loss, and that's how you would go about the training. So I know this part of the video at least, wasn't that much about the model. The thing is, the model is very, I mean, it's pretty not, it's not that modern in terms of the fact that it's not cascading or ensemble. It's not that unique, but I mean, it worked really well for them because they got first place in 2020. So yeah, that's pretty much it for this paper. The next paper is automatic brain tumor segmentation with scale attention network. And I want to start off by going through one of the papers that this paper talked about in the related work section. And that was an ensemble network. An ensemble network essentially is a combination of models. And the reason why you have this is to increase the performance, the accuracy of the models. Now, for instance, there might be some disadvantages to models that other models can solve. So, for instance, in this case, models with large receptive fields may show improved localization capabilities, but can be less sensitive to fine texture than models emphasizing local information. So there's some disadvantages to some models, but there are strategies to handle these imbalances, which can be done with another parameter from another model. And that's why when combining these models, you're kind of, in a way, creating a super model of different models that have a lot of information with them, and when combining them all together, it's going to create a lot better accuracy. So this paper that was in the related work section, it talked about 3 different models that it used, and then it combined them together to form an ensemble model that they called EMMA, which I'm pretty sure would be Emma. So first you start off with the deep medic model architecture. And long story short, you're taking the input that has normal resolution and low resolution, you're passing it through convolutional layers, then fully connected layers, and you're combining them together to get a segmentation. So that's the deep medic. You also have a fully connected network, which is over here, and the U-Net model, which you should also be familiar with. Now, for both of these, they have pretty similar components in terms of the convolutional layers, the strides, the max pooling, the upsampling. So in terms of that, the components are very similar, though you can see that the model architecture is not. So you have those 2 models as well. So now you have 3 models in total. What the ensemble part comes in is, with these models, you're taking the output that you have for all of them, and all the outputs are the class confidence maps. So what's the confidence that this is a tumor core? What's the confidence that this is a whole tumor? So you have class confidences like that, just like you would in a single neural network. But now you have 3 maps of them because you have 3 different models. So the final segmentation that's created by Emma is performed by assigning each voxel in the class with the highest confidence, just so that you can aggregate all the information that you have and make sure that there's a consensus on which one has the highest confidence. And from there, you would just have a pretty high accuracy, as shown in that model. Now, off the related work, back to this research paper and the model that it had in this. Now, it looks fairly similar to the U-Net model, but to be completely honest, it is not similar at all. It was actually really complicated to understand as well. Now, for the encoder part, you have the residual net blocks, right? And those have the 2 convolutional normalization ReLU layers side by side. And then you have that skip connection as well, as you can see over here. Now, not only do you have a ResNet block though, you have a squeeze and excitation module embedded within the ResNet block. So looking at this, this is how it works. You have a function that's given into the input convolutional block and the number of channels that it has. So over here, you have the width times the height times the amount of channels. And this is just assuming that this is a 2D image. Now, you squeeze each channel to a single numeric value using average pooling. So over here, you would just squeeze it to a single numeric value, or which is C in this case. Now you have a value R, and this is where it gets really important. This is the most important part of the squeeze and excitation module. You have the value R, which takes the output channel complexity and it reduces it by a certain ratio. And in this case, in this paper, it said that the ratio, I believe, was R is equal to 4. Yes, that is correct. So R is equal to 4. So you're dividing the number of channels by 4 here, by 4 here, and then you're going back to it with the sigmoid, and then you're scaling it, and then you have the same thing that you would have with the ResNet module that I talked about at the beginning. So that's pretty much a squeeze and excitation module. And you see that it's repeated here once, then two times, that's in the encoder, and then you have the bottleneck, and you're going back up the decoder. And in terms of the decoder, now, yes, you do have the ResNet and the squeeze excitation modules as one in each scale, but you also have the transpose convolutions, which is probably what you've already heard with the U-Net models, because on the left-hand side in the encoder, you're going through the downsampling layers, and then you're going back the upsampling layers in the transconvolutional layers. So that's one thing that is fairly similar in terms of comparing U-Net and this module. Now, after this, you also do have these skip connections, right? You already had skip connections from before, but before going to these skip connections where you're doing these summations, you actually have scale attention blocks. And this is where the research paper got really complicated, because you have scale attention blocks happening 4 times right before each block in the decoder. And this is what it looks like. I mean, you might understand it, but I definitely did not understand it, and it did not take a very short time. So I'll try to explain it, although there might be some gaps in my understanding. So first of all, you know how you have these dotted lines. Now all of these dotted lines, they represent scales. So this is scale 1, scale 2, scale 3, and scale 4. And you can see that they're all connected to the scale attention block. So over here, when you take the scale 1, scale 2, scale 3, scale 4, you're just directly taking whatever was here, and then you're putting it through here. So that's what you're doing. Now you have this value of 2, and the way they explained it in the paper is that this value of 2 is equal to the variable d, and then the value for the scale is equivalent to the value of variable e. So now you're comparing e and d. If e is less than d, which in this case it is, then you use the max pooling plus convolutional layer, and that is that's for the e is less than d. For e is equal to d, which is in this case, you basically do nothing. And then over here, when e is greater than d, which is when 3 is greater than 2 and 4 is greater than 2, then you apply the trilinear upsampling after you do the convolutional norm value block. That's what it says in the paper. So you have to go through that. Now, after you go through this, not only are you you're doing the element-wise summation of this, the concatenation, but you're also taking the values and you're putting them over here, because this will also represent the scale as well. So over here, you're going to be doing the element-wise multiplication, but you can't do that unless you go through this part as well. Now for this part, this is actually kind of complicated, because first, what you're going with is you're doing a spatial pooling layer. And a spatial pooling layer, as described here, if you think about it as an analogy. Let's say you have a face, the face is zoomed in, it's rotated, it's tilted, you have some sort of modifications and variations of the face. The face is still the face. Now, a model that spatially rigid and doesn't have spatial pooling features embedded into it, it won't be able to recognize the feature. Now, if you have spatial pooling though, then it'll just make the model more resilient to minor shifts in terms of the position, in terms of the orientation, because multiple positions are pooled together. And this is actually an example of it, of how it works. And then you see that there's fully connected layers. And that's actually what happens. So after you go here, you have more squeeze and excitation modules as well for each scale. And then you're going through a softmax scale layer, and then you're going through a fully connected layer when you're element-wise multiplying it by the weights and then the values that you have. And then you're doing the element-wise summation to get the end. And that's essentially what's happening over here, where you go through the scale attention block, then the summation, and then you move on to the model. And then all of these combined, you get the output, which you can then compare the loss and try to do the backpropagation stuff for that just to make the model more accurate. So that was this research paper. Implementation, the convolutional layers instead of max pooling layers would be beneficial because, first of all, they would save memory. There's no need to map the output of the pooling layers back to the input when you're doing back propagation, because then you're going backwards and just trying to map it out, right? Now, instead, what you can do is, instead of using these unpooling layers to map it out, you can use deconvolutional layers, because you're going to be using deconvolutional and convolutional layers anyways, so you might as well stay consistent to save memory, and you wouldn't have extra functions that are quite unique from what's happening in the model. However, as I mentioned a few seconds ago, it depends on the specific implementation, and the paper doesn't specify or give any sources onto what that specific implementation would be when you would use max pooling instead of convolutional layers for the downsampling. So I guess it's just a matter of knowing what works better for the model, and I guess for this model it worked better if it was convolutional layers instead of max pooling layers. So aside from that, you're basically following the same thing. You're going down when you're trying to increase the amount of channels this way, but then also decreasing the dimensions. And then you're doing the same thing here when you're going up, and the up is actually a deconvolutional layer. So you're trying to now increase the image dimension so that you can reach that same dimension of 128 by 128. So then you're going up, and now you're decreasing the amount of channels so that you can reach 64 channels as well. That would match the input and the output. And then from there, you would also have this, which is the element-wise sum of this, and then you're just going to concatenate it over here with this part of the decoder. And this should be quite familiar because in the U-Net models, you also have the same thing where you're concatenating information from the encoder to the decoder. That was pretty much it in that sense. And then over here, what ends up going different is this part where you have the 1 by 1 by 1 convolutional layer. And that's just helping to get it into the right format. So when you put it through the softmax, you can easily get the probabilities. I think that was pretty much it for the model. It also did talk about how skip connections would be beneficial, but if you already knew about U-Net, it's mostly the fact that the convergence is easier and it's more accurate that way because you're feeding in information from the past into the present. So that's a pretty good analogy if you want to think about it that way. But that was pretty much it for this model.
The last paper I read was E1D3 U-Net for brain tumor segmentation. And the really cool thing about this model is I've been looking at models that have the encoder-decoder architecture or are variations of the 3D U-Net or V-Net model. Now with this one though, not only do you have the encoder and decoder, you now have the encoder and 3 decoders, hence the name E1D3 U-Net. So in this, the components are pretty similar, especially to the last paper that I talked about. And you start off with the input and you go through the convolutional instance norm and leaky ReLU block. And that's all in one. And then you repeat it 2 times until you go downsampling through a convolutional layer. And as I mentioned in the previous paper, if you have the stride of 2, you're just decreasing the dimensions like that. You don't need the max pooling, and there's certain advantages to that as well. Then you're following the same pattern of trying to increase the amount of channels while trying to decrease the dimensions until you get to this point. And then from this point, you go on to go to these blocks, this one, and this one, where you apply the same convolutional instance norm and leaky ReLU function, and then you move on to going upsampling. So with the upsampling, you're using transpose convolutions, and you're also using a stride of 2 for this. So now you're increasing the dimensions, but with the ones that are concatenating and then you're using the other convolutions, you're now decreasing the amount of channels. That's pretty much what happens in any U-Net model if you think about it. So it's pretty much the same phenomenon, except it looks a bit more complicated because now you have 3 duplicates of the decoders that are ending up with a binary segmentation output of the three different classes that you want, which in this case were going to be the enhancing tumor, the tumor core, and the whole tumor, those three. Now you have those, but in order to form this whole segmentation, like you have here, when you fuse them together, you need to do that fusion. And so to do that fusion, you have some sort of label fusion procedure that you would use. And this model talked a bit about this too. It was a bit confusing to understand, but the very high level picture is you're just adding on all the binary segmentation maps that you have and trying to fuse them in a way so that you end up from something like these three to something like this. That's pretty much it for this model.